All right, some videos, or a video at least, for week 13. We introduced 2 degrees of freedom systems. Here's some examples of 2 degree of freedom systems. The first on the right hand side, pretty typical, where we have these masses and springs, and so each mass can be considered have an associated degree of freedom with it in motion. We could also have mixed ones where we have like maybe the suspension of a car, and so really the 2 degrees of freedom are the displacements at each of these points A and B. We can, instead of using those coordinates, have the displacement of the center of gravity and an angle. So it still remains 2 degrees of freedom, but those are better measures of the motion. Some other ones, we have these pendulum. I'll do an example, or there's an example in the book of these pendulum that have a weak spring that connects these two. So if they were just independent of each other, they're not really 2 degrees of freedom system. They're not really a system. So it needs this spring in between the two that makes some kind of connection, so the motion of each of the 2 degrees of freedom are related to each other. In this case, we would use the angles θ1 and θ2 to be the degrees of freedom. And I'm not quite sure the one on the left, if this is what they're implying here. Since there's no spring relating these two things together, I'm not quite sure if this would be considered a real system, except I guess maybe the rotation. Okay, I see it now. We have the stiffness of the torsional stiffness of this bar, the torsional stiffness of this bar, and the torsional stiffness of that bar. But they should all be related to each other and come back to just 2 degrees of freedom, θ1 and θ2. That's not much different, actually, from the rotational and torsional stiffness between each of these shafts and the moment of inertia, mass moment of inertia. They're using I. Sometimes we use J instead for the mass moment of inertia. But in this case, the 2 degrees of freedom are θ1 and θ2. And this is here's a compound pendulum with a θ1 and a θ2 as well. We can mix them up where we have a displacement of this box, or this crate or block, or whatever you want to call it, that's on little frictionless wheels, but it also has a mass pendulum on top of it. So we have the degrees of freedom be mixed with translational and this rotational. And then this lathe, this isn't actually all that much different from the car suspension, where we would have actually the motion of the center of gravity and the angles right there. Here's a 2 degree system, which has both motion in the x direction and the y direction, and there's going to be some amount of coupling that are going to take place. It's got to be a coupled system. The motion in the x direction would have to influence the motion in the y direction, but I guess maybe we would have an angular or a diagonal motion might be somewhat related here. I think this actually can make the case that these are uncoupled from each other, depending on for when they're treated as a simple type of problem. All right, so we have this section 5.1 of our textbook. We have the normal mode analysis, right? So this is a typical type of thing. I'll note that you should really draw the FBD and the IBD of each of these pairs on here, just to double check that you're getting them correct in terms of the coupling. One of the most important aspects of this, let's try to see if I can, well, I guess I'll use the highlighter or the pen. I use maybe I'll use the laser pointer. Okay, this guy right here, you'll note that if this serves as your FBD, this is going to the left, but it's the same identical force that's coming to the right when you're writing out these equations right there. And you really should use an FBD and IBD pair to make sure you get it right. All right, let's see. It won't let me. I guess I'll just go to is this the next one? Okay, there you All right, so what we would do here is assume a form, a solution form, where they both have it times the sine of the natural frequency times the time, but we're going to have a different amplitude for each of these. So we could substitute those in. Notably, they skipped a step. So I would write this in a different way. I'd alternatively write out this initial set of equations up here. I'd write them into matrix form, and then I would say, here's my solution form in the x1 and x2, but also as x double dot 1 and x double dot 2. And then we would substitute that in there, removing the x1 and x2 from this setup, and they're all going to share the same sine of omega nt right in there, and so could bring that to the outside. So we will do that into the next setup right here. You'll see we get this into matrix form. We get basically the same thing there as we got. Let's see if we can make it back as we got right there, right? So those should be the same. All right, so and notably I also got rid of the sign because that shouldn't be equal to 0. So both of these things have to be equal to 0, and A1 and A2 don't have to be equal to 0, so we can just ignore those and take the determinant of what's inside the brackets. And when we do that, and we also replace omega 2, which is the natural frequency, by lambda, just for convenience, so we can see a characteristic equation right here. So we put this together, and we use FOIL onto this. We could see also dividing by m, by mass. We're going to be able to find two roots, and from those roots we'll be able to find these values. And remember that right up here we took omega and squared and set that equal to lambda, so now we could reuse that back again and find these become the natural frequencies. We don't know what K and M are, but we still have two different natural frequencies because of the arrangement. Now we could go back and we could find the eigenvectors, right? So those are the eigenvalues. Now we find the eigenvectors by replacing one of the two. Or I said plug in one of these natural frequencies back into the original equation to find the relative amplitudes A1 and A2. These are the eigenvectors, the mode shape of each of the natural frequencies, and we can rearrange them to find this ratio of A1 to A2. So we take the top row right here, multiply by A1 and A2, and that's where we get this equation right here. And we rearrange these to be A1 over A2. And then we can plug in one of the solutions, right? If you go back to one of the two solutions, easier to go back to the lambdas because they are already the omega squared. So I'll plug that back in, and you'll note that all the k's will cancel out right here, and the k and the m's, and we end up with this. And that's going to be the ratio for the first natural frequency that we plugged into there. That's be this guy. We plugged him in, and so A1 would be equal to this, and A2 would be equal to 1, right? So it's showing you the proportion that A2 is going to be larger than A1. You could do the same thing again, but this time plugging in the other natural frequency into that same equation right here, and you get negative 2.732. So what this tells us is that we're going to be out of phase, and A2 is going to be smaller than A1, right? So up here, A1 smaller than A2, and they're in phase with each other. They're moving back and forth in the same direction at the same time. And this one right here, they're going to be moving away from each other. And just in case we're curious, you don't have to do this next step. We could take this row right here times this column for this equation. Also set A1 to A2, and also plug in the natural frequency, and we get the same thing, right? The little 6 falls off because of some round off error. And similarly, we could plug it back in. So we only have to do one of the rows times the column to be able to get what these eigenvectors are. And another way to write them is to write them as a vector right here, right? Because you could see that there's A1 over A2, and we just treat A2 as equal to 1 right in there, and the same 2. But in MATLAB or in other places where you would get an eigenvector, they would be their magnitude would be they would be divided by their magnitude so that they were unit vectors, and so their magnitude is now equal to 1. But that's just for your information. We don't have we can go ahead and use this format right here, no problem. Right there. So the mode shape I would describe from these eigenvectors could probably better be described by taking I just took 4 locations here, at the end points are equal to 0 here, so you kind of see the relative magnitude of the motion of x2 is greater than x1 in that mode 1, and then in mode 2 that the magnitude, the motion of point 1 of this of position 1 is in the opposite direction and greater than that of mode 2. So I think that it makes more sense to me to have this written out in that format. Okay, so I'm going to go on. Let's see what the next slide is going to be. All right, no moment is in phase. Yes, that's good. And 2 is out of phase, and the mass is as we've seen right there. So I will let those 2 stand for right now. We will bring these up again, and we'll look at these again in class or in week 14, just a little bit more. I will now we'll make a new video for the rest of this lesson.